help. So we sound how. Yeah, that hour and 90. You were just talking about
I see.
Costco, right? One.
Right. As George mentioned, there is this restless motion of particles. Spin for 13 billion years never slow down. So Yoshitaka Hatta from PNL is going to talk about spin, this motion, form factors, and GPD.
All right. Everybody, nice to see you all. I'm Yoshitaka Hatta from Brook, also Riken Research Center based on Brook. I'm going to give you 3 lectures. And I changed the title, obviously. Roughly divided into 3 categories. First, about nucleon spin physics. I will talk about polarized DIs, things like that, and the form factor and the GPDs. So before introducing the physics, let me introduce myself. So I got a PhD from Kyoto University, 2004, 20 years ago, and I did my first postdoc at the Riken PNL Center, so Brook. And then I moved to Saclay, was in France. So I did a postdoc about 4 years. Then I got a faculty position in Japan, so I went back, and then was in Tsukuba, University of Tsukuba for 5 years. And then I moved to Kyoto University, where I graduated. And then I moved back to the United States, to Brook in 2018. And my research interest is basically the physics explored at the Electron-Ion collider, the hardware structure from QCD, and nucleon spin physics, nucleon mass, 3-dimensional and 5-dimensional tomography, and also small x. I'm interested in many things. So this is the Electron-Ion collider project, and this is a next generation nuclear physics facility. It's your generation, basically, next generation nuclear physics facility to be built at Brook National Laboratory, New York. So we are somewhere around here, and only 30 minutes by car. Brook National Laboratory is there. This is a rig. So this is currently a rig. There is a rig ring here, about 3 or 4 kilometers long, and my office is somewhere around here, down there. As of now, this is the only new high-energy collider in the world officially approved for construction. And the main physics goal of this EIC is QCD. Okay? So this is very unique, because if you think about LHC, for instance, the main physics goal is the physics beyond the standard model. And QCD is a tool to discover the new physics, but this machine is different. The QCD is the main thing. So it's the QCD first machine, and the mission is to unravel the structure of the proton nuclei. And there will be many lectures later in this week and next week, so I will not talk about too much about this. I will mostly, but let me just show that these are the scientific goals of the EIC. So this is from the influential National Academy of Science report, which was crucial to get the EIC approved. And so the committee identified 3 major problems to be addressed at the EIC. How does the mass of the nucleon arise? And how does the spin of the nucleon rise? So my lectures covers the second bullet to some extent. And finally, what are the emergent properties of dense system of gluons? This is mostly about gluons, small x gluon saturation. There will be a lecture by Yuri Kovchegov and other people later in this course. So that's the overarching goals, but I want to get into the details, because this is a school, so I want you to develop some skills in addressing these problems. Okay, so this is my plan. So I start today mostly covers with the proton spin decomposition problem. I assume that you know nothing about this, but maybe some students are very advanced in this direction, but I basically assume nothing about spin physics from you at the moment. And then I introduce polarized deep inelastic scattering and how QCD can theoretically explain this polarized DIS. And then probably the first two bullets is what I'm going to cover today. And then tomorrow, orbital theory of orbital angular momentum. And then we move on to the generalized parton distributions, and also the deep reversion photon scattering, which is sensitive to the generalized parton distribution. That will be tomorrow's lecture, or maybe tomorrow and the day after tomorrow. And finally, I will talk about form factors, nuclear form factors, fast electromagnetic form factors, and also the gravitational form factor, which is a kind of hot topic right now. Or maybe I should talk about form factor first, but somehow when preparing my lectures, I ended up with ordering. All right, so that's kind of introduction, and I'll get to the details. So, but before going there, here's my notations. Everybody has his own notations. So, but this is my notation, and so this is a metric, G mu nu, mostly minus metric, which is standard in the QCD community. And when I say ij, it runs from 1 to the transverse coordinates, perpendicular to the direction of beam, energy beam. I use the light cone coordinates, p plus minus. Oh, but by the way, this slide is on the web, so you can download it, so you don't have to take notes or anything. Okay, so this is a light cone coordinates, p plus minus, and some people, this is my convention, and some people do without this 1 over square root of 2, so you have to be careful when you're reading a paper. And in these coordinates, cis notation G plus minus equals 1, upper index is plus, and the index becomes minus lower index. And for a vector product of 4 vectors would be like this. And also people have different notations for different conventions for gamma 5. So this is my notation, which I think is the same as the Peshkin and the epsilon tensor. People have different conventions, or and this is for the transverse 2-dimensional antisymmetry. So this is 1 and 2 x and y basically. And people have different notation for the coupling constant of the QCD. So some people have minus Ig here. I use plus Ig, and then this sign is reflected into the sign of the Wilson line here. So the sign here is correlated with the sign here. So people use different notations, so you have to be careful, and then you should establish your own notations. All right, so here's the problem, the proton spin problem. So we start with the very basic facts, two facts. The proton has a spin 1/2, and yeah, proton is not an elementary particle. So these two facts immediately implies that the spin of the proton 1/2 can be decomposed into the spin and orbital angular momentum of the constituents. So there is this quark has helicity, quark has spin. So that contributes to this delta sigma term, and gluons have spins, so call it the helicity, and double contributes to this delta G. And this is, and there is orbital angular momentum of quark and gluons. So all this, the combination of these components should add up to 1/2. And I will show you how precisely this decomposition can be made in theory. Okay, so that's basic. So we want to understand this. So I want to explain to you the theory behind this composition this morning. All right, so to get this first, my starting point is QCD angular momentum tensor. So of course, QCD is a Lorentz invariant field theory, right? So the QCD Lagrangian is invariant under the Lorentz transformation. And whenever there is invariance, there is an associated current, the conserved current. So the current associated with this Lorentz transformation is called angular momentum tensor. So these are three indices, so and it's mu, nu, lambda, but this is conserved, but conserved only with respect to the first index, mu. Okay, and there are two other indices here, and that's because Lorentz transformation involves two tensors. So the omega mu nu comes with two Lorentz indices, so that's why you have extra nu and lambda indices. So this is a three-index tensor, but it's conserved only with respect to the first index. So this is very basic things. Whenever there is invariance, there is a current. And if you look at, so you start with the Lagrangian and you do this Lorentz transformation, and then you should be able to derive this net of currents associated. And this is how it looks like. This is called the canonical, I would call it canonical angular momentum tensor, which has a term depending on the coordinates. So because here you have a coordinate here, x nu. So there is a term which depends on this coordinates x. And the coefficient is called the canonical energy momentum tensor, which looks like this. So yeah, so these are energy momentum tensor associated with the translation or invariance of the Lagrangian. You can recognize a term which looks like co-orbital angular momentum because here you have x and here you have a momentum. So it's a cross product between coordinates and momentum. So that these first two terms represents orbital angular momentum. Okay. And then the same with the same for the gluons. So you have this. This can be interpreted as a momentum of the gluons. And so this is a cross product between position and the momentum. So that's the gluon orbital angular momentum. And then there is a spinor part. So there is a term which corresponds to the quark helicity, like this one. And there is another term which corresponds to the gluon helicity. So already at this point, this already shows you the four-term decomposition of the nucleon spin, actually. So there are four terms, quark orbital angular momentum, gluon orbital angular momentum, quark helicity, and gluon helicity. So I've already accomplished this spin decomposition theory. So here's the exercise. Since this is a school, I will give you many exercises along the way. So first exercise, derive this form, derive this QCD angular momentum tensor, starting from the QCD Lagrangian. So I'll give you a hint. So use this relation. So if you do the Lorentz transformation, then the coordinate changes. And so this is a variation of the fermion field. So you have a term which is associated with the coordinate change. Okay, so this is coming from this this coordinate transformation. So there is a term like this. And then, but this is not the end. There is actually another term which is related to the fact that the fermion field has a spin 1/2. So not only the coordinates, but also the field itself changes under the Lorentz transformation, right? And the way it changes depends on the spin of the field. So in the case of fermions, you have this gamma matrix commutator here. So that's a spin 1/2 representation of the Lorentz group. And in the case of vector fields like photon and gluons, you have this coordinate term, which is coming from the coordinate transformation. So the coordinate is shifted, so you have this shift, and another term which is related to the fact that the gauge field is spin 1, and the spin 1 field transforms like this. So there are two terms, so you have to keep both of them. And then finally, also the Lagrangian itself transforms, and Lagrangian it's a scalar, so there's no spin part; it's just a coordinate transform. So use this formula and then derive this canonical angular momentum tensor. So that's I leave it to you as an exercise. All right, so we derived it, but this thing. However, there is a problem. It's not so simple. So well, maybe some of them already recognize that this energy momentum tensor is not gauge invariant, right? You have this ordinary derivative here. So if you do this canonical procedure, then you end up something unphysical, in the sense that it's not gauge invariant. So you have this ordinary derivative, that's a problem. And also here there's ordinary derivative, and you have this A field, which is also not gauge invariant. So that's a problem. And also this T mu nu is not symmetric. Okay. Well, we used to think that the energy momentum tensor is symmetric with respect to these two indices, mu and nu. But if you derive it in this way, then it's not symmetric and it's not gauge invariant. And the second problem, which is related to the first, is that the T mu nu is conserved with respect to the first index, but it's not conserved with respect to the second index. So that's another problem. All right, but anyway, it's gauge dependent. But it's gauge dependent, but let's then interpret in a particular gauge, and that's called Jaffe-Manhart decomposition, which is a relation that I showed you at the beginning. So this is equation for us basically by picking up the plus 1, 2 component of the canonical angular momentum tensor. So this has free index. So mu is plus, nu is 1, and lambda is 2. Then take the matrix element in proton state, and then you can achieve this decomposition immediately, starting from this canonical momentum tensor. It's not gauge invariant, but let's leave that issue aside for the moment. I'll come back to this point. So as I said, this is not gauge invariant, except, however, this co-helicity term, which this is gauge invariant. Okay. So this is a local operator, so this is gauge invariant, so that's fine. But the other three terms are not gauge invariant. You see this Gluon helicity, you have a J field here, so that's obviously this is not gauge invariant. This is canonical orbital momentum. You have this ordinary covariant derivative, ordinary derivative here, so that's not gauge invariant, and Gluon canonical orbital momentum. And you might think that what if you just replace this covariant derivative with the why not just replace this ordinary derivative with the covariant derivative? But that's not the answer, actually. Well, maybe this is fine, but you cannot solve this problem of gauging issues by if you just replace this delta by D, it's still gauge dependent, right? Because you have a field here. So that's not the way you go. So it's a non-trivial issue, and this is a well-known problem. How you define the angular momentum of gluons in gauge theories like QCD. All right, so but let's just interpret in particular gauge, which in this case is called a light-cone gauge, which is A plus equals to 0 gauge. And in this case, there is a pattern interpretation. So you have you can think of this as a partonic decomposition of the proton spin. All right, so I want to get deeper into this direction, and then first I need some definitions. So here's the definition. So spin, you can think of it. You usually think of it as a vector in 3 dimensions, right? But you can generalize the spin vector into 4 dimensions, and here's the definition. So here's the definition. So this is a ferrosome spinner. It can be electron and proton, any spin 1/2 Dirac spinner, and they form this combination here. And this is S mu. This is a spin. This is called a spin 4 vector, which you may not. Which, for example, Peshkin doesn't explain this 4 vector, but as you can define like this. And then this delta sigma, the clock helicity contribution to the proton spin is defined like this. So this is this is a proton single particle state. And this is a QCD operator, which represents the helicity, and then some over the clock flavors. So here's exercise. So starting from this definition, show these 3 relations. Okay. And the first relation might be trivial. This first one is easy, but the last 2 might be it's not so trivial. And I give you a hint. Can I?
Good.
Okay. Well, let's start with the third relation, because if you can prove the third relation, then you can prove the second relation. So I want to go with the third relation. So you probably have seen this elementary formula, right? Okay, so this one you can find it in Peshkin, but this one I haven't summed over the spin. I keep the spin index open, so I'm not summing over spin. So this is a kind of generalization of this formula. Okay, so how do I derive that? So I use the Fields identity. Well, probably there are many derivations, but let me use the Fields identity. Which says that any, so you can think of it as a 4x4 matrix. Right? Dirac spinor has a 4 components, and this is a transpose of the Dirac spinors, which also have a 4 components. So this is basically a 4x4 matrix. And you can decompose a 4x4 matrix in the complete basis of 4x4 operators, which is provided by the gamma matrices. So you can, it's a kind of Fields identity. So you have a term proportional to the unit matrix, and you have term proportional to the gamma matrix, and then another term which is coming from the gamma 5, and then it's a minus sign. Actual vector term. And then finally, there is the tensor term. Okay, so this is a Fields identity. You can always decompose a 4x4 matrix using the complete set of 4x4 matrices, which I take it as a gamma matrix. All right, so this is identity. Then I can move on by writing this. This is 2m, right? Okay. 2 times the mass. I'm using the capital M, but it's the same. And then this is 2 times p mu. Now the third term, this is actually 0. Think about why it's 0, but it's 0. And then the fourth term, this is by definition 2 times the spin vector, right? That's my definition of S mu. So the same thing appears here. And the last term, this is the most complicated term. You need some, this is the most non-trivial part, but I can tell you this formula, which is another exercise. Is equal to okay, try to prove this relation, which is another exercise. And then you should be able to derive that relation immediately. Once all this is set, then that's basically the derivation of the third relation. And the second relation, you can solve, you can prove it by using the third relation. So that's I leave it to you. All right, so this is basically the basic tool to this spin vector shows up in the rest of my lectures. All right, so okay, so coming back to this relation, so this is a definition of delta sigma, which a quark helicity contribution to the proton spin. And if you think of proton as a naive, just a three quark system, then you can explain this 1/2 by saying that okay, two of the quark have a spin up, and the last quark has a spin minus, and then you can this immediately concludes that the delta sigma is 1, and the rest is 0. But this is based on the static quark picture. But if you consider, you can also consider the orbital angular momentum of quark inside a proton, like in the bug models. Then you find that the delta sigma is 0.7, which is 70% of the proton spin coming from the quark helicity, which is still a significant amount. All right, so this is a naive theory prediction that the delta sigma is 1. So and you can actually measure it in experiments by doing, you can measure this delta sigma in experiments by using the deep inelastic scattering. So here's the basic process. You have a proton and muon or electron scattering, and then electron emits a photon, virtual photon, and it hits a proton, and the proton shatters and fragments into a bunch of hadron in the final states. And probably this is too elementary, but there are two basic kinematic variables. One is the Bjorken variable x. It's defined like this. So q is the virtuality of the photon and divided by the speed of q. And you can write it like this by introducing the invariant mass of the final state x here. And of course, this mx is bigger than mp, which means that x is always less than 1. Okay. Whatever final state you produce must have an invariant mass larger than the original proton state. And then if you go to the high energy, if you go to a very high center of mass energy, then this denominator, so p plus q is basically the center of mass energy. So this x goes like q squared divided by s. And this is a small x region. Which will be, there will be lectures about this. So something dramatic happens when you go to this small x region, but this lecture, I'm not getting there. And the physical meaning of x is basically the momentum fraction carried by the struck parton, which you can immediately derive it from by considering these elementary kinematics. So think about the quark coming out of the proton, carrying the momentum fraction psi, and absorbs the photon, and this is the final state quark momentum. And if you require that this is on shell, like this, then you can immediately see that this psi is actually equal to this x variable, which you can determine in actual experiments event by event. So that's basically the physical meaning of it's a momentum fraction. So that's why this is less than 1. All right, so what you can measure, the simplest thing you can measure in this experiment is a so-called structure function, which is kind of a total cross-section. And here's the operator definition of the structure functions. You have two cases: unpolarized scattering and polarized DIS. Polarized means that the proton beam is polarized in longitudinally or transverse directions. So in the unpolarized case, you have two structure functions, F2 and FL, and assuming that the QCD conserves parities. But if you also include a weak interaction, there will be additional terms. But then this talk is mostly about the polarized DIS. So in this case, you pick up the asymmetric part in this mu indices. So the unpolarized case, you pick up the asymmetric part, but in the polarized case, you pick up the antisymmetric part. And then again, you have two structure functions, G1 and G2. So this will be the this will be the main topic of this first lecture. I'm going to give you a theory of G1 and G2. All right, so another exercise. So here's the forward Compton amplitude. this is a time-ordered product of incoming photon and outgoing photon. So if you consider, I'm talking about the total cross-section, so I square the amplitude. I square the amplitude here, and then you have two photons, one in the amplitude, then other in the complex conjugate amplitude. So the total cross-section is basically given by the correlation function of these two photon currents. And this tensor can be decomposed into the symmetric part in indices mu nu and the antisymmetric part in mu nu. Okay, so I put the I here for some for convenience, but you shouldn't be confused. This is not the real imaginary decomposition. Okay, so TA and TS are both complex. Okay, so this might be confusing, but this is actually standard. When you read the papers, you might be confused, but so this I is just a convention. So this is not the real imaginary convention. This is a symmetric, antisymmetric decomposition. Okay. And on the other hand, so this is a forward amplitude, but the total cross section is the imaginary part of this. You have this optical theorem. So you take the imaginary part of this one, and so this then you get what you get is a hadronic tensor. It's called the hadronic tensor. So instead of a time-ordered product here, you have a commutation relation here. Okay, then again you can decompose it into the symmetric part and antisymmetric part. And this time, this S, WS and WA are real. Okay, so this is a symmetric, antisymmetric decomposition, but at the same time, it's the real virtual decomposition. Okay. Now the problem is that starting from this definition, show that the imaginary part of TS is WS, and the imaginary part of TA is WA. Okay. So that's the exercise. I don't give you a hint. So, but just start from this formula, and then you can assume that the Q0 is positive. That's kind of crucial to get this structure. But yeah, so you should use definition of time ordering. So you should introduce a theta function and then decompose, explicitly write down this time ordering, and then okay. So that's an exercise, which is kind of non-trivial. It's not so obvious, right? All right, so I want to analyze this time-ordered product of currents in the limit of large Q. So because in DIS, large photon virtuality, you should be able to use the perturbation theory. So I want to analyze this function in the limit of large Q square. However, at the same time, when I send Q square to infinity, X, the Bjorken variable, is assumed to be constant. So this is called the Bjorken limit. And the analysis of structure function is possible in this limit. So I want to study this correlation function in the limit of large Q. So naively, because this Q is very large, this integral over y should be dominated by the small y. So roughly, because roughly speaking, y goes like 1 over Q. But that's actually not the case. As you can see immediately, by looking at this process in the rest frame of the proton. So in this frame, you can write this X like this. So this is the proton mass, and the numerator is like this. And in the high energy limit, suppose that the photon is moving in the minus direction, then this first Q3 minus Q0, this is large, and this cancels with the denominator, and you have this here. Now, given this, then you can estimate what values of y will be contributing to this integration. So y plus is indeed small. So because y plus goes like 1 over q minus, and 1 over q minus goes like this, and then x is fixed, and q squared goes to 0. So y plus is indeed 0 in this y plus integration. But if you look at the y minus integration, y minus is conjugate to 1 over q plus, and q plus is actually fixed, right? So you cannot assume that y minus is small in this when you do these integrations. But on the other hand, this naive expectation is correct if you consider the invariant. So y square goes like 1 over q square. So the invariant y square goes to 0, but that doesn't mean that all the components of y goes to 0. Oops.
click on that.
Oh. So that's a caveat. That's an important caveat. So you necessarily have this non-locality in the y minus direction, and that's that there you can make the connection to the pattern distribution function, which is also non-local in the y minus direction. All right. So the basic two. Okay. So keep this in mind, and then let's do the operator product expansion. So if you have the product of current. And then supposedly this short distance behavior, so y square goes to 0 is important, so I can do the operator product expansion. And this is basically given in the lecture notes for the Peskin textbook. This is the equation number. I'm just copying the same equation here. And so basically do the contraction between two quark fields. You can do it in two ways. So this quark fields, or you can do it in this quark fields and that quark fields. Okay, so there are two terms. Okay, so it's the same equation. Now, in the Peskin's textbook, you have this product of three gamma matrices, and in Peskin's textbook, you pick up these first three terms here, because they are talking about the unpolarized DIS. But in my lecture, I'm talking about polarized DIS, so I pick up this last term, which is coming from the involves the antisymmetric tensor here. Okay, so that's something new to you. Then so I decompose this three gamma matrices and then pick up this last term, and then you have this and this is my OPE result. Okay, so you can see this infinitely many operators are contributing, right? So it's increasingly numbers of derivatives involved. So n is the number of partial derivatives here, which you can promote it into the covariant derivative actually. And but at the same time, higher dimension operators are suppressed by higher powers of 1 over q squared. So one might naively think that the most important operator would be those with the smallest dimension. So the smallest n would be dominating with this operator product expansion. That's a naive expectation. However, because of this light codominance, the situation is a bit different, because you might think that so large q's higher dimension operator will be suppressed by 1 over q squared, but the numerator might also be large. And that's what happens. So we are taking this built-in limit, and in the proton, if you take the proton matrix element, then this derivative will be replaced by the proton momentum. So there will be you have q dot p. So derivative becomes p. So you have q dot p in the numerator, and that's divided by q squared. But this is not small. This is 1 over x, which is fixed, right? So in fact, infinitely many operators are contributing, and that's the difference from the usual operator product expansion. So what you have to expand, not in terms of the dimension of the operator, but you have to expand in terms of the so-called spin, the so-called twist, which is defined by the dimension of the operator minus the spin of the operator. And the spin here means a Lorentz spin, but in practice, basically it's a number of plus Lorentz indices. Okay, so for example, this looks like the same operator, but this is twist 2, which you should keep, but this is twist 3 because this has a transverse index, and so in our field, spin basically means number of plus indices. So the most important operator is the twist 2, which is coming. So this is a twist 2 polarized quark operator. You have as many derivatives as we wish, but all these indices are symmetrized, and also the trace is subtracted. And there is a gamma 5 here, so that's a polarized twist 2 quark operator. So these operators, there are infinitely many of them are contributing to the operator product expansion. You have to keep all of them in this Bjelken limit. So here's the okay. So you have many operators, and then you take the proton matrix element from the left and from the right, and then you can parameterize this matrix element in this form. So this is a unpolarized case, which you can find in Peskin probably. then you have this constant an, but the Lorentz structure is completely determined because this is totally symmetric vectors. And sorry, excuse me. This is not unpolarized case. This is a polarized case, but twist 2. Okay, so this is symmetric in all the indices here, and the available vector is P and S. You have a speed vector also, so you can parameterize like this is the most general parameterization of this matrix element of this operator, and then we have P dot Q, which is converted into 1/x here. And you have this AN, this is an unknown non-perturbative constant, which you can determine from experiment. Okay, so this is a symmetric twist 2 contribution. This is the most important terms. And there is also a twist 3 terms, which is one twist higher. You can make twist 3 by making one pair of indices antisymmetric. So this one symmetric in all the indices, but this is antisymmetric between lambda and the rest of the indices. So there is a lambda here. So you want to make this lambda to be antisymmetric with respect to mu1 and mu2. And this is twist 3. It's one twist higher. And then you have this antisymmetric combination here, and they can compute the parameterize this matrix element again using this available vectors P and S. And you have a different coefficient here, dn times 1/x here. So that's so if you remember the definition of G1 and G2, then you can convince yourself that this twist 2 part is contributing to the G1 and G2, but this twist 3 term is contributing to the G2 structure function. Okay.
Right.
Yep.
So what does so when people talk about like higher order twist things, what physical picture does that translate?
Physical picture. Well, higher twist means that suppressed by large scales. Higher simply means that they suppressed by 1/q to higher powers. So this is twist 2, but you can continue this dot here. You have infinitely many operators, which is higher twist. And if you take the matrix element of that operator, then plug it into the cross section, then you find that it's suppressed by 1/q to high power. So it's a subleading contribution, which I'm not keeping this except this twist 3 terms for the G2 structure. All right, so I have now I have shown this parameterization, so then I can derive the G1 structure function. So this is how it looks like. So this is by definition the imaginary part of this current correlation function, right? And it's given in terms of this AN that I defined in this relation. So this is AN, and using this AN, compare with the definition of the G1, then this is what you get. Now, this AN, you can write it in a quite different way. Remember how AN is defined. You can write it as a matrix element of this high dimension twist 2 operator. So this is a twist quark, polarized twist 2 quark operator. Its matrix element is basically the AN. So you can write it like this. And you have the sum over infinite many terms and take the imaginary. But there is an obvious problem here, because so there are two problems. Number one, you have this infinite series in powers of 1/x. And as I told you, x is less than 1, right? So 1/x is bigger than 1, which means that this series is divergent. Okay, so that doesn't make sense. And number two, you see all the terms are real. There is no imaginary part whatsoever here. So superficially, this doesn't make sense at all. Right? All the terms are real, and it's not convergent. So something is amiss. So as it is, it doesn't make sense. But let's try to make a sense out of it. So here's how you proceed. What do I do? Okay, so let's first write this infinite sum in this form. Okay, so here I introduce a non-local correlation function. So this is a local operator, but here I introduce a non-local operator by introducing this Wilson line. Okay, So here's another exercise. Start from this, show that these two formulas are equivalent. Okay, it's not, is it not obvious? So well, you can just use partial integration. So this k plus, so I introduce a dummy variable k plus, and this k plus can be converted. If you do the partial integration, it can be converted into the derivative acting on this phase factor. And then again, do the partial integration, and this derivative acts on this Wilson line, and that produces this covariant derivative. So these two expressions are equivalent. And then you write this infinite sum. Then you can perform this infinite sum, because n is here and there. So you can do this infinite sum and get this expression. But it's still real, right? But once I have done this infinite sum, then I can do the analytic continuation. So original series was divergent. It converges only at the unphysical region of X. But now I have done this infinite sum, I can do the analytic continuation from large X to small x in the physical region. And the rule is to use this add a small imaginary part to the X, which has to be minus I epsilon. So let me explain why it has to be minus I epsilon. So the scattering amplitude usually scattering amplitude is a complex function of Mandelstam variable, right? And what we define as a scattering amplitude. So if you plot the scattering amplitude in the complex plane of the Mandelstam variable, there is a cut in the real axis. And you usually define the amplitude to be above the cut. So you add the one minus epsilon term here. And so this is a usual, this is how you define the scattering amplitude. And now if you remember this definition of X, then I told you this is 1 minus Q square over S. So I have to shift S to plus I epsilon, which means that X is has a minus I epsilon imaginary part. So this is why you have to add minus I epsilon. I'm talking about sign in front of the epsilon here. So this is a rule. You have to do it like this. And then so I add a small imaginary part in the previous expression here. So here there is a X here, and so X should be X minus I epsilon. And then there is an imaginary part. So I can pick up the imaginary part. And then this is the result. So what is defined here is polarized clock distributions, which is commonly denoted by delta Q of X. And you have another term, which is X going to minus X. That's the polarized anti-clock distribution. So G1 structure function gets contribution from clock and anti-clock in the same way. And yes, and so here's the definition of polarized clock distribution. So you can derive it from the operator product expansions. One caveat here is that the anti-clock PDF, you have a plus sign. So this is there is a minus sign difference. So this is in the case of unpolarized clock and anti-clock PDF, this is a relation. And in the case of polarized clock PDF, there's no sign. This is a little caveat. All right. And then, okay, so another exercise. So now that I have an expression, so this is a G1 structure function. And starting from definition, I show that the nth moment of G1 is proportional to the AN that I've defined before. Okay. So this constant AN is basically the moments, the many moments of polarized. What time did I start? 11?
Still have 15 minutes or so.
15 minutes. Okay. I should hurry up. All right, so that was for G1, and then we can do the same thing for G2 structure function. So that will be it's more complicated because it is partly twist 2 and partly 3. So maybe this is another exercise that you can just repeat the same thing for the G1 and show that you have this formal expression here. So again, this is the sum of infinite terms, which is not convergent. And also all the terms are real. The same story here. So you should be able to derive this. And then this coefficient here is actually the moment, nth moment of the G2 structure function. Okay. So this AN, so one interesting thing is that this AN is basically the same AN that you find in G1 structure function. So this G2, and there's actually a relation between G1 and G2. So here's, well, maybe this is another exercise that, so start from this. So this is a relation for the moment, but you can invert this moment relation and get a result, this result for the G2 structure function, which is first derived by Wanzura-Wycheck in 1977. This is called the Wanzura-Wycheck relation. So the G2 is actually related to the G1 structure function in this way. So you have the minus G1 and some moments of G1 here. So the first two terms is related to G1, and that is called the Wanzura-Wycheck part. It's related to the twist 2 PDF. And then there is another term, which is twist 3, and that is related to this D coefficient here. That's entirely twist 3. And the physical meaning is that this is not beyond the part of picture. So you have, it's not a two-body correlation function, it's a three-body correlation. So quark, anti-quark, gluon correlation function. Now, for example, the most famous relation is the second moment of this extra term, G2 bar here. The second moment of this G2 bar is called G2. And that is this matrix element of psi bar F psi. The quark, anti-quark, gluon, twist 3 operators, which is first derived by a professor in the Stony Brook. Question?
Yeah, yes, hold on. When we talk about twist 2 within the leading power, right? But the next leading power, like all over the Q squared expression is twist 4.
Yes,
Twist
for
3 is
polarized case.
Okay. Or polarized with mass. Okay, but twist 3 it's 1 over Q, right? It's not over.
Yeah, 1 over Q.
Okay.
Yes, so I'm talking about the polarized DIS, and in the case of polarized DIS, you get a twist 3 contributions. In unpolarized DIS, you have a twist 4. You don't have twist 3. Okay. So yeah, so this G2 is a complicated object which has both twist 2 part and twist 3 part. And there is an effort to measure this G2 function from double spin asymmetry. I think JLab people have been measuring this and try to extract this G2, D2 coefficient. All right. Well, maybe this is another exercise to show this relation, which is very non-trivial. Okay, so that's the theory part. So let's come back to the experiment. So here's how you get delta sigma from experiment. So the observable is it's called a longitudinal double spin asymmetry. It's called AAL. So this is EP scattering. Well, I put mu on because this was the original experiment by the European Muon collaboration. But you can also do it for electron, of course. And then basically this electron and the proton are both longitudinally polarized. So in the spin pointing in the same direction or the opposite direction. And you take measure the cross section and take this asymmetry. So you have a parallel, so this anti-parallel spin configuration cross section, and parallel spin configuration, and take the asymmetry here. And this ratio can be related to this G1 structure function. So this is how you extract the G1. And as I said, this G1 can be written in terms of the polarized and quark and anti-quark distribution function. But I didn't tell you that in practice, there is this E square term, right? Because quark has different charge. So up quark, down quark, strangeness, they have different charges. So that's actually a complication. So you have to put back in this E square terms here. some of the different flavors. So that brings you a lot of headaches because so you have to decompose this factor into the SU3 basis. So this is, let's consider the 3 flavors. So you have up quark charge 4/9, and this is down quark charge -1/3 square. It's 1/9, and strangeness 1/9. Right? And you have to decompose this matrix into the basis of SU3. So you have a term which is proportional to the unit matrix, and there is a term proportional to the T3, the third generator of SU3, and there is a term proportional to the T8, the 8th generator of SU3. So you have to decompose like this. And what we are interested in is delta sigma correspond to this first term. It's a flavor singlet combination. So what you can measure, left-hand side, you can measure it from experiment. On the right-hand side, you do the theory decomposition. So you have a contribution from singlet and isobector term and octet pieces. So you have to disentangle these 3 contributions, and of course there is a higher order correction of order alpha s. But so you want to extract the first term, but the second and third term you can extract it from elsewhere. Okay. So this second term basically the matrix delta U minus delta D. You can derive it. You can estimate this term by using a neutron decay experiment. So this, in fact, this is called G3. This is one of the most famous low energy constant in hadron physics. This is a proton matrix element of the third generator of SU3, the flavor SU3, and it so happens that this G3 is exactly the same as the matrix element that you probe in neutron beta decay. Okay, so here you have a proton. You see the difference here. You have proton, and here you have proton and neutron. Okay, and you have up and down, and you have all the quark flavors here. So it's a totally different matrix element, but somehow by using these 2 matrix elements are related by the SU3 symmetry. Okay, so maybe this is another exercise to show that. Okay, so you can actually and from the neutron beta decay, you know this constant GA very well. Maybe you can compute it from lattice QCD. So you know the second line, and the third line is you can also get it from elsewhere. This time you can get it from this hyperon semi-electronic decay. So there is a baryon called Xi minus, which is composed of 2 strange quarks and 1 D quark. And this baryon decays into lambda, and you have this non-perturbative matrix element here. So psi baryon going to lambda, and you have up quark operator, action vector operator, which is composed of up quark and strangeness. And somehow, by the group symmetry of SU3, this matrix element is the same as the proton matrix element of the octet generator. Okay, so this is again the consequence of SU3 symmetry. And so if you measure this process, this decay, then you can get this G8. And so you can estimate this third term and second term from a neutron, and then finally you can estimate this delta sigma term. Okay. Yes, so this is what people did in 1987 at the European muon collaboration. So it's a muon. So as I said, that's why I put the muon here, because this was the original experiment. They used the muon. And this muon is it's in the name of the collaboration. It's a European muon collaboration. This was 1987, and they did this experiment, and they subtracted the garbages, and then finally this is what they get. So delta sigma, which is supposed to be 1, turns out to be 0.1. And if you consider the error bars, then it is consistent with the 0. So that was the first measurement, and everybody was shocked. People call it the spin crisis. Yes, so that's where the spin physics began. Actually, this is the beginning of the new field, which continues to date. But this original estimate was quite a bit of an underestimate actually, but more recent value points to a larger values, it's like 0.3. It's 30% of the proton spin coming from the quark spin. But then the question is what is the rest of the spin coming from? Maybe okay, so all right, so of course, so we have a quite bit accurate measurement of delta sigma by now. And the next question is a Coulomb spin contribution. So here's the definition. So delta G is integral from 0 to 1 of the polarized Coulomb distribution function. So previously I talked about the polarized quark distribution, but we can also get the polarized Coulomb distribution function. And here's the definition. You have F and F tilde. So in the case of unpolarized, you have FF. But in the case of polarized Coulomb, you have F and F tilde. And you have very nice physical interpretations of this operator, which I think was derived by Manhwa in 1990, I think. So you can write this operator in the following suggestive form by introducing the polarization vector of the Coulombs. Okay, so this is a polarization vector, right-handed and left-handed Coulombs polarization vectors. So you can write its operator in this form. So this is a right-handed Coulomb. So this is literally means that the number of right-handed Coulombs minus the number of left-handed Coulombs. That's a net polarization. So that's why this operator proves the helistic contribution, Coulomb helistic contribution. There's so that's a nice physical interpretation, but there is a very peculiar aspect about this, because if you take the moment of this delta G, then what you get is not the local operator. So previously, if you take the moment of PDF, you get a local operator, but that is not the case here. If you take the first moment, and you still have a non-local operator. That's a very unusual thing. It's only this operator. All the other operators reduced to the local operators. And there's ambiguity when you do this X integration, because you have this 1 over X, right? So you have to specify the prescription, how you do this 1 over X. And also there is an X here. So this is 1 over X times this exponential, and then you integrate. What you get is a theta function or principal value, or theta y or theta minus y, depending on how you avoid this 1 over X pole. But it doesn't matter actually, because the result will be independent of this prescription on this 1 over X. You should be able to convince yourself about that. But in any case, whatever you do, you get a non-local operator, and that's very unusual. Even after taking a moment, you get a non-local operator. And this is a very peculiar feature of this delta G. But it reduces to the local operator if you work in the light cone gauge. So if you set A plus equals to 0, then this non-local operator collapses into a local operator. And what you get is actually nothing but the Jaffe-Manhwa delta G. So here, that's the, right. Maybe this is a good point to stop. Oh, okay, so maybe also show you the current status. So there has been a lot of experimental effort at Brookhaven and the other places. So how do you measure this delta G in the experiment? So again, you do this polarized. This time you do the polarized proton-proton collision. So Rick can do that. Yes, they have been measuring this for the last 20 years at Brookhaven. So Rick is a PP collider, polarized proton-proton. So again, you take the double spin asymmetry, the double longitudinal spin asymmetry, and take the difference, the same polarized in the same direction and opposite direction, and you have a accuracy factorization. You can write it in terms of different contribution from quark and gluon, polarized quark and polarized gluon contributions. So, and the final state is typically a pion, but more recently they have managed to measure the photon asymmetry in this experiment. And then this is a press release from my colleagues at Brookhaven that basically they determined that the delta G is positive most likely positive from if you integrate from certain region of X. So this was a press release. Okay, so and at the same time, of course, the global analysis has been running, and or maybe this is a bit already old result. So there are three major collaboration: DSSV, NMPDF, and JAM, and they all point to a positive gluon helicity if you integrate from finite region of X, but there is a huge uncertainty from the small X regions. Very difficult to access the small X region in the experiments, but there might be a very big contribution from the small X region, and that somehow revived the interest, the community, in the theory community, and how to understand the small X behavior of this delta G, for example, perturbation theory. And I think you're gonna maybe you're gonna hear that from Yuri's lecture, or maybe he doesn't talk about this, but in any case, he's the driving force in pushing this field. This was the status until a few years ago, but just last year, all this previous analysis was based on the next leading order global analysis. But finally, just last year, next global analysis became available finally. So I have to update this result. So this is not the most. This is not up. Yeah, not up to date. All right, so that's it for today.
Can you go back to slide 26? What's the definition of this F-til?
Oh, there. Oh, sorry. This is other. You do or you explain things.
When you were doing the flavor decomposition, I guess I just,
This one?
yeah, at what point did we assume the heavier quarks don't contribute to G1?
Well, in this formula, I'm already assuming that one, right? So, well, in principle, you have a contribution from Cham quark and maybe bottom quark, but that's usually neglected. And for the Cham quark, the contribution from Cham quark to the unpolarized BIS has been evaluated. There is a global analysis, including Cham quark, but I have never heard of Cham quark contribution to the polarized DIS. I've never heard of it. Maybe Fred, do you? Okay, but
I don't think it's ever included in
yeah,
analysis.
people assume that it's very small, but
I guess maybe why is it assumed that it's,
well, okay. So in the unpolarized case, the Cham quark contribution is 2%. Okay, and I don't know in the polarized case maybe some anomaly, but naively maybe 2% corrections. I haven't seen anybody taking that into account, so maybe that's a new project out of it.
Of course, there's other pairs.
Which means it doesn't contribute.
Yes.
Yes.
I guess.
Yeah, you can include the Cham contribution diagram, for example. All right. I haven't seen the role of Cham in this context.
So I was wondering in the colonial framework, we have like the valence structure, right? Does this still hold for the polarized case? So is the up quark still in the large X-ray 2 times the output? Or count?
I don't have there should be an instruction, but I don't have a plots. But these plots are available. I don't remember the shape of the delta U, delta D. It's peaked around 1/3. I don't know.
Let's keep on.
Okay, so we can still think of it as not way in the code.
At large X, yeah.
We'll have uniform check next week. That should tell us what's going against 4x. That's how.
Yeah, also this polarized PDF are not necessarily positive. Very good.
So if I can have a follow-up, so on slide 21. So this relation with Q minus X is bar X that relates to the small X region.
No, this is for generic X. This is just a definition. It's not the application. This. You mean this one? So, sorry.
Yes, so I'm a little confused because the in unpolarized the anti-quark is kind of different from the half-quark if you take the Q, for example, as the quark. So I was a little confused about this equation, in which limit it holds.
This relation?
Or just the left equation.
This one?
Yeah.
What do you mean? This is just a definition. So Q over X is this the same except this gamma 5 here. That's the unpolarized PDF, which is a function of X from -1 to 1, and we interpret the minus X negative X region as a anti-quark PDF in this way.
The relationship between quarks and anti-quarks.
Yeah, it's just a definition.
Where those densities, because then you do this X support is going to be from -1 to 1. Because we always say, oh, X pure is from 0 to 1. Yeah, but it's not that.
Okay.
Pure, it's from -1 to 1. -1 to 0 is what are your anti-quarks. 0 to 1 is what are your quarks. It's just the.
Yeah, so this is an unpolarized quark PDF definition, and this function, as a function of X, it has support between -1 to 1. So positive X region we interpret as a quark PDF, and negative X region we interpret as anti-quark PDF.
Welcome. All right, any other questions or comments? Okay, so you have your homework, but you're not going to do your homework now because we'll have lunch. Okay, so Fred, what do we do? Do we start slightly later?
Yeah, I think so. What's a good time?
1:15?
1:15?
Let's start at 1:15. But before we go for lunch, let's thank Yoshitaka for this technique. Lunchtime, I think Fred is.
So I'm going to head over to the Stony Hall where you can use your meal card. So if you want to follow me, let's see, we're going to lock this room. So you can leave anything here and it'll be secure. We'll lock that up